If you look at a modern airliner engine, it is easy to assume the raw power comes from the fiery exhaust in the back. But the internal component of the engine burning the fuel does not generate the majority of the aircraft's forward thrust. The heavy lifting is done right here at the intake. That large fan at the front is responsible for pulling in a massive column of air and accelerating it backward to propel the plane forward. To understand the efficiency of this system, we measured the bypass ratio. This is the volume of air routed entirely around the internal engine core, compared to the volume of air that passes directly through it. This cross-section shows the ratio in action. On a modern engine like the GE9X, the bypass ratio is roughly 10:1. 10 kilograms of air bypass the core for every single kilogram that enters it. Accelerating a massive column of air by a modest amount requires less energy than taking a tiny amount of air and accelerating it to extreme speeds. This is the fundamental physics of propulsive efficiency. Moving that large mass of air at a lower velocity is also why high-bypass turbofans are significantly quieter than older turbojet designs. However, larger fans require significantly larger, heavier nacelles. These structures must be carefully integrated to maintain sufficient ground clearance beneath the wing. The physical footprint of the fan dictates efficiency, but it creates immense aerodynamic drag and weight challenges for the airframe. To drive a fan of this magnitude against the resistance of the air, the internal core must act as an immense, highly concentrated power source. While propulsive efficiency happens on the outside, paying for it requires pushing internal thermodynamic limits to the point of destruction. The engine core operates on the Brayton cycle, a thermodynamic sequence that defines the performance of gas turbines. The cycle runs in 3 steps. First, incoming air is compressed. Next, heat is added at constant pressure by burning fuel. Finally, the resulting hot gas is expanded through a turbine to extract work. Efficiency in this cycle is dominated by the overall pressure ratio, the factor by which air is squeezed before it reaches the combustor. On advanced engines like the GE9X, the overall pressure ratio reaches 60:1. This means the air is squeezed to 60 times its original atmospheric pressure before combustion. The second critical factor is the turbine inlet temperature, the heat of the gas hitting the first stage of the turbine immediately after it leaves the combustor. The turbine blades are forged from nickel-based superalloys. These metals maintain their structural integrity only up to roughly 1100 to 1200 degrees Celsius. This creates a thermodynamic paradox. While the metal fails around 1200 degrees, the gas temperatures entering the turbine routinely exceed 1500 degrees Celsius. The combustion gas is hundreds of degrees hotter than the melting point of the metal components it flows across. In a theoretical Brayton cycle, without active intervention, the engine would instantly liquefy its own first-stage turbine. In this regime, the turbine operates as an active system of thermal survival, designed to exist in conditions that would liquefy standard hardware. The blades in the first stage face a combined threat: extreme heat and massive centrifugal stress from spinning at thousands of revolutions per minute. Standard cast metals are comprised of microscopic grains. Under severe stress, the boundaries between those grains become natural weak points. This leads to creep, the slow, catastrophic stretching and cracking of metal under sustained load. In a turbine, creep starts specifically at these microscopic grain boundaries. To combat this, engineers use a highly controlled manufacturing process to cast each turbine blade as one continuous single crystal. By eliminating grain boundaries entirely, the single crystal blade achieves extreme resistance to creep deformation. Without this integrity, the centrifugal force would cause the blade to elongate until it smashed into the engine casing. Single crystal casting solves the mechanical problem of stretching, but a piece of nickel will still melt if exposed directly to a 1500-degree gas stream. The second layer of defense is active internal cooling. The turbine blades are heavily hollowed out to allow airflow. High-pressure air is bled off from the compressor and routed into the base of the blade. It moves through an intricate internal maze of serpentine passages to draw heat out of the metal. That cooling air is then forced outward through tiny holes drilled into the blade's surface. This creates a process called film cooling. As the air exits, it sweeps over the outside of the blade, creating a boundary layer of cooler gas that insulates the metal from the main combustor exhaust. The final defense is a specialized thermal barrier coating applied directly to the metal. This ceramic layer is only 1 to 2/10 of a millimeter thick, yet it can reduce the temperature of the underlying metal by up to 200 degrees Celsius. Every bit of air bled off to cool the turbine is air that cannot produce thrust, which directly lowers the engine's total thermal efficiency. To reduce this penalty, engineers are shifting towards ceramic matrix composites. These materials tolerate far higher temperatures than metal, requiring significantly less cooling air. This represents the ongoing effort to run the Brayton cycle hotter, while reducing the parasitic drag of the cooling systems required to sustain it. In the end, an operational turbine blade functions simultaneously as a load-bearing structure, an internal wind tunnel, and an insulated ceramic shield. Theoretical models still require engineers to validate these environments through physical testing. Because tiny aerodynamic anomalies can disrupt the protective film cooling, the fluid dynamics of the gas flow must be perfectly predicted and measured. Testing records reveal the tight tolerances of design iteration, where temperatures are pushed right to the threshold of failure to maximize efficiency. Every single incremental gain in overall thermal efficiency inherently demands more exotic materials and tighter, significantly more expensive manufacturing. It is a continuous chain of engineering constraints. Because pure jet thrust is efficient at moving an aircraft, we construct extremely large fans at the front. To physically drive a fan of that size, the system requires a highly pressurized, ultra-hot core. Those required core temperatures mandate the implementation of single crystal alloys, active internal cooling, and thermal coatings. The modern turbofan is a stacked architecture of integrated constraints, an engineering chain where each individual layer exists to physically solve a limitation exposed by the one before it. To explore the deep engineering concepts that drive modern technology, visit ProReadyEngineer.com.